Hello students, welcome to today's session of Daily Chemistry Dose. Today we shall be discussing one topic of Raoult's law from the chapter of solution of plus 2, and along with it we shall also be taking some aspect of isothermal distillation. So before I go into the details of this particular topic, I first have to explain it to you what basically do we mean by vapor pressure. So this is very important to tell you first, then we will place a question in front of you. What exactly do we mean by vapor pressure? Pressure exerted by the vapors of liquid at equilibrium in a closed container. This is a general definition which we people know. The vapor pressure is the pressure exerted by the liquid at equilibrium in a closed vessel. Say for example, if you have some evacuated vessel, into this you added some liquid. Into this evacuated vessel you added some liquid. So if you would see, and you are going to maintain the temperature of this system at T Kelvin, and now if you would see the pressure goes after some interval of time, you would see some pressure coming here. This pressure is because of the vapors which is being produced within this system due to the establishment of equilibrium between the liquid and the vapor, and this pressure we call it as vapor pressure. Now let me explain it. What does it mean? So it simply would mean this thing, that if say for example you have this liquid A, pure liquid A is put into this evacuated vessel at temperature T, what would you see? That if you have started with A moles of liquid A, after some interval of time what you would see, that to begin with there is no vapors. At after time T1 you would see X moles of vapors, and then at after time some other time, some more interval of time, so you would see A converting to A minus Y becomes Y, it would give Y moles of A vapors, and then it becomes Z and Z. And if this, now we can say after time interval of T3, you would see that this Z moles of vapors are not changing. So we will say here the equilibrium is established. Equilibrium is established because you could see a constancy coming in the number of moles. Now what does it mean? At this point of time, if I have to write the pressure P1, it is X RT by V. I am assuming vapors to behave like ideally, just like a ideal gas, and I am placing it this way, that the P1 at this point of time, what the pressure gauge is being showing it to me is XRT by V, and this at P2 this is YRT by V, and here at P3, which I am saying it is a equilibrium pressure now, this would be ZRT by V. Here I would make it very categorical statement here that this volume which I am taking is not the volume of the vessel, it is the volume of the vessel minus the volume of the liquid, because this is the only place where the vapors are there. If the volume of liquid is negligibly less compared to the volume of the container, you can ignore it. Otherwise, religiously saying this volume is the volume of the vessel minus the volume of the liquid or solid, whichever pure form you have taken. So as a matter of fact, here I'm just ignoring the fact that volume is not substantially changing with the change in change of liquid into the vapor. So I'm considering as it to be same during this process. Now what exactly do I mean here is that this is a physical equilibria, and for this physical equilibria, if I have to define some equilibrium constant, this is a physical equilibria which we have wrote, and for this physical equilibria, if I have to define some equilibrium constant, so I would say Kp, which is partial pressure of A as vapors, which is equal to ZRT by V. This is what you get. So I can say this has to be equilibrium vapor pressure. So vapor pressure in itself is a point. You can say these P1, P2, P3, this P1, P2, P3 are nothing but vapor pressure, but this is key, this is going, this keep on going increasing till the time it would not achieve an equilibrium. You cannot define this pressure, although before reaching the equilibrium this can be said as vapor pressure, but technically saying that equilibrium pressure is the pressure which is attained at equilibrium, because then you would see constancy in every property. Thermodynamic variable has become constant. Now the fact of the matter is that if this container which is containing a liquid at some temperature T, if somehow if I increase the volume of this container, if I increase the volume of this container, what would happen? This volume has been increased from, let's say, from V to V dash. This volume has increased by decreasing the pressure, keeping the temperature constant, because I am not going to change the temperature in whole of this discussion. So now if volume has been increased, so then this equilibrium got disturbed. I will say now you have to write it as QP. What is QP from the point of view of physical equilibria chapter? So we say ZRT by V dash. This volume has been changed. And since V dash is greater than V, we will say that QP has becomes less than KP. Now, as per the Lee-Chatelier principle, when a system would have uh, QP less than KP, this particular equilibria, which we have written it as a liquid in equilibrium with a vapors, so this equilibrium would shift forward, Now the question is, for how long it would keep on going forward? Equilibrium would shift forward till QP again become equal to KP. So this equilibrium is forward driven. So matter of the fact is, you have to remember that the vapor pressure, equilibrium vapor pressure, is corresponding to equilibrium constant Kp, and if you disturb that system at temperature T by decreasing its pressure or increasing its volume, the liquid would convert into vapors more till the time QP becomes equal to KP. So here comes the question which would have that feel with you, that this particular discussion which I have just have done, without that discussion you cannot be able to attempt this particular question, and the video would be little lengthy because this particular question is being asked somebody from the south who is preparing for IIT Advanced. So just to give him a answer to this particular question, I thought of placing it onto the YouTube so that more students could get benefited from this. So here comes the question. So this is the question which is being asked, that there are two liquids A and B. There are two liquids A and B which are forming a ideal solution at 300 Kelvin. So what you have taken is the liquid solution containing A and B, for which mole fraction of A is 0.6. So they have taken a container. Let me take it like this along with it so that you can understand pictorially also, because that is very easy and good way of explaining the things, because if you could see it pictorially, that you have taken A and B here in this system. Let me place it somewhere more here. Okay, so this is what they have done is, just let me write it once. So this is XA is zero point 0.6 and of course XB would be 0.4, and this container is fitted with a piston where the pressure can be varied. So it is, this liquid is taken in this container where XAXB mole fraction is being given in the liquid state. Now this is the important statement which you have to focus on. The solution is slowly vaporized at 300 Kelvin by decreasing pressure starting from 1 atm. So the solution has been slowly vaporized by decreasing pressure. Now how pressure they might have decreased? By increasing its volume. So when the volume has an increase, this liquid present inside it would start evaporating, or this would start going into the vapors. This is what the viewpoint would be. That is why I have discussed the effect of lowering of pressure onto the equilibria in terms of vapor pressure. So this equilibrium would shift forward in the sense that both of these liquid would change into vapors. Now the question is, what is being asked here is, calculate the mole fraction of A in the last droplet of liquid. Okay, so since this liquid, you keep on decreasing the pressure by increasing its volume, keeping the temperature constant. Now this is also very important that the temperature is kept constant here, that the conditions are made isothermally, but as you increase the volume or decrease the pressure, the liquid is going to convert into vapors, and for converting liquid into vapors, it has to overcome intermolecular forces for which some energy is being lost, as a result of which the liquid's temperature should fall. But you must have some reservoir which would be constantly supplying it a heat so that the temperature is maintained at T. So as a matter of fact, simply you have to focus it that the conditions are maintained isothermally. So now this liquid A and B are getting converted into vapors, and when all of this vapor has been all of this liquid has been converted into vapors, this is what you have left with is the last droplet. Now this last droplet, for this last droplet you are supposed to find XA dash and XB dash. This is what the question is. That at you started with XA 0.6.4. This is the starting, and when this pressure has been decreased, this liquid keep on going into the vapors, and then at the last droplet you have to find the mole fraction of A and B in the liquid state. This is what the question is. It is quite challenging question. It would take a bit of more time. So this pressure is 300 and 800 torr. Once you get on to the concept, the problem solving or the numerical solution for this particular question is very easy. It would hardly take 1 minute, but the concept clarity would take some time to explain. Now here comes the discussion. Now this can be easily understood on the graphical way. So first you have to understand on the graph that how it is to be interpreted. First, this is being given as this is XA, which is 1, and if XA is 1, this XB would be 0. Here XA is 0 and XB is 1. So this on this side you have a vapor pressure. So this is the vapor pressure of pure B, this is the vapor pressure of pure A, and what you are being provided with a liquid where XA and XB are being given as 0.6 and 0.4. So XA, XB are given as zero point 0.6 and 0.4. Now what else now you have to start with? You have to remember that this is a line which is showing liquid composition, and this is the line which is showing vapor composition. Now this first you have to understand what are the things you have to focus on. So if I say that at this point here somewhere here is the pressure is 760 torr, say for example, that is 1 atm pressure at this point of time. So at this point of time, both A and B, whatever vapors they have been condensed and they are in the liquid state. Now you are decreasing the pressure. Once you are decreasing the pressure and you would reach this point is the point where first bubble of vapors, a bubble which would contain A as well as B in vapor form, that bubble would get expelled from the liquid state, and once it got expelled, then the molecules of A and B got separated into the vapor. But to begin with, first bubble which came out of the vapors containing A and B, corresponding to that, what is the vapor phase composition? So first on the graphical way you have to understand this is YA YB. Now what is YA YB? It is the mole fraction of A and B in vapor state corresponding to a liquid composition of liquid composition of A and B in liquid state when it is 0.6 and 0.4. Corresponding to this is the vapor phase composition. This is first you have to understand. Now, so this is what you can call it as the first bubble, or bubble point also is very popular in discussion, but bubble point in fact is a temperature at which the first bubble containing the vapors has been expelled out from a solution containing two or more components. So now this is the composition, vapor phase composition above this liquid containing 0.6 mole fraction of A and 0.4 mole fraction of B. So corresponding to this, there must also be some pressure here. This where there would be some P total here. This pressure would definitely be less than 760 and definitely be greater than 300 torr. So what is that? That also can be asked in the paper. Now what they are asking you is, let me show it in another way. Now if you want to show that what is the pressure at which first bubble pressure, which is not being asked, let me show it, pressure at which first bubble of vapor came out. So how to find out? So this would be P total is equal to PA plus PB. We are just applying the Raoult's law, that is P naught A XA plus P naught B XB. Now everything is being given to you. P naught A is 300 into 0.6 plus 800 into 0.4. So this comes out to be 500 torr. So this is the pressure that at 500 torr, when the pressure is decreased from 760 to 500 torr, you end up getting a bubbles, first bubble, which would have this vapor phase composition. Now since you know the P total now, corresponding to this P total, you can also evaluate the vapor phase composition of first bubble. So if you want to do that, let me do it that one also. So here we shall be writing once again the same statement, and I hope you people know that PA, if you happen to write partial pressure of A using Raoult's law, the formula is P naught A XA. Now Raoult's law is applicable for solution. This is applicable for solution. What do I mean by solution? That vapor pressure of A from Raoult's law can be evaluated by multiplying mole fraction of A in liquid state. Mole fraction of A in liquid state multiplied with vapor pressure of pure A. And PA could also be determined from Dalton's law. And Dalton's law is applicable for vapor state. So this is very important to tell you. Dalton law would be applicable for vapor state. Raoult's law is applicable for the solution. So what is PA for this? It is P total into mole fraction of A in vapor state. P total into mole fraction of A in vapor state. That is Dalton's law. So since both of these can be used to find the partial pressure of A, so we can equate them together. So we can say P total into YA is equal to P naught A XA. Now if I have to write YA, it would become, what is P naught A? It is 300. What was XA? It is 0.6. And what was P total? 500 torr. So corresponding to this came out to be 0.64. YA came out to be 0.64. Sorry, it come out to be 0.36. Sorry. And YB comes out to be 0.64. That makes sense also. Now see here, what I'm saying is, this value came out to be 0.34. If I just write it here by rubbing it, so how much is this value came out? This came out to be 0.34, although this is not being asked in the question, and this is 0.64. Obviously that the vapor phase composition, because if XA is 0.6, it is less volatile. Since it is less volatile, or rather I would say B is more volatile. B is more volatile, so the mole fraction of B in vapor state in the first bubble would be larger. That is also a very interesting point to tell you. Now coming on to the next statement. The next statement was, we wanted to find out the last droplet composition. Now let me place it once again for you. Now the point is, this was XA, which is 0.6. Now you have to be patiently trying to understand, because once you get to know this graph, you are through the answer. So at this point, this is 500 torr. At 500 torr, this YA and YB happen to came out to be 0.34, and this came out to be 0.64. As simple as that. Now what you shall do? Earlier it was 760 torr. 760 torr applied on this composition, it is having totally liquid. When you decrease the pressure, when you started decreasing the pressure by increasing the volume, liquid start converting into the vapors. Now as it goes down to 500 torr, first bubble came out containing the vapors of A and B, and that vapor, when expelled out of the liquid and came out of the liquid into the air or into the empty vessel, then they produce this composition of A and B. Okay, now if you decrease the pressure further by increasing the volume, so you would reach this point also. Corresponding to this point, now this can be said as XA dash. Sorry, this would be said as, sorry. Now, since I am saying here, it should be drawn here, XA dash, this is XB dash, because this line is telling me the liquid composition, and corresponding to this would be YA dash YB dash, as simple as that. Because once the vapor start coming out, which liquid would go first more in quantity to begin with? It is B is more volatile, so in the liquid state A would be left. So what you are able to see is, in the liquid state, composition of A started increasing, because XA on this side is 1 and XA on this side is 0. This you should remember. On this side it is 0. So in the liquid state, the composition of A started increasing and B started decreasing. Now, if you decrease the pressure further down, so if you decrease the pressure further to this point, let me show it with, let's say, red marker. If you reach this point, what is this point? This is the very important point, very important stage where you have reached. You have decreased the pressure by increasing the volume. Liquid kept on going out as vapors. Both A and B bubbles are coming out, and you would reach a point where now you would have this liquid. This is the last droplet of liquid. Wow, last droplet of liquid. And corresponding to this last droplet of liquid, I can say this has to be XA dash and XB double dash. And corresponding to this red dot is the vapor phase composition as YA double dash and YB double dash, which happens to come equal to that of 0.6 and 0.4. Wow, this is the only statement which we have to figure it out, and you are through the answer. What I'm trying to explain it once again, let me explain it once again. What I'm trying to say, that when you kept on decreasing the pressure, both of these lines are moving towards the left side, less towards the A composition. What I'm trying to say is that when the pressure is being decreased, volume is increased, liquid went to the vapors, the composition of the liquid state start getting enriched in A. Now, when the last droplet came, the vapor phase composition corresponding to last droplet has become totally equal to that of the composition of mole fraction of A and B in the liquid state when we started at 760 torr. This is what you are supposed to see into it. Now, once you get to know this, that the composition corresponding to last droplet has a vapor phase composition exactly the same as that of A and B in liquid state when we started with 760 torr. That is what you have to now see into it. Now, what we can do here is to find out the answer here. Let me write the same statement once again, that P naught A XA is equal to P total YA. This is the general statement we used to write. Now, if I am able to just would change in such a way that I would get the answer in a speedy way. So, what I can say here is YA is equal to P naught A XA upon P total. This P total can be written as XA P naught A XA plus P naught B XP. This is what we have already done. A little of mathematics, if I do, you would get the answer very fast. So here I shall also be writing this as to be 1 minus XA. So then the equation would turn up to XA plus P naught B X P naught B plus P naught B XA. So from here I, so there should be negative sign here. So this would become negative, and now if I place it this way, YA is equal to P naught A XA upon P naught A minus P naught B XA. In some other video, I will show you some other graphical way of interpreting these equations. So this is a very important equation which tells us at any point of time what is the vapor phase composition. So what we are interested to know, what we got at last drop, at last droplet, we found that corresponding to last droplet, this is what we are interested to know. This is what is being asked, and what we know is this thing. So I may say corresponding to last droplet, my YA double dash is zero point 0.6, XA double dash I am not aware of, and P naught B I know. So I can say 0.6. So this is my now YA dash would be written like this. This is P naught A XA double dash upon P naught A minus P naught B XA double dash plus P naught B. This is a very useful expression. So now what I can say is 0.6 is equal to 300 XA double dash I don't know. This is 300 minus 800 XA double dash plus this is 800. So if you solve this out, you would end up getting, if you solve this out, this XA dash comes out to be 0.8 and XB dash of course then would be 0.2. So this is very interesting. So this value came out to be, this value came out to be 0.8 and this came out to be 0.2. As a matter of fact, at this point of time, if we wanted to find out the P total corresponding to this pressure, so corresponding to pressure at last droplet of liquid, how much is that pressure if it is being asked? This would be, again you can find it out like simple way, this XA dash, this is P naught XB double dash. So this is 300 into 0.8 plus this would be 800 into zero point 0.2. So this comes out to be almost 400 torr. So what basically you happen to get here, corresponding to this point, the pressure has been 400 torr. Now another question you may be asked is, between 400 to 500 torr, if they give you some pressure, say for example they ask you that what would be the what would be the what would be the composition of liquid and of vapors, when, say for example they say when P total is 450 torr. So that can also be written 450 torr is equal to P naught A XA dash plus P naught B XB dash. So XB dash can be written as 1 minus XA dash. So this is 300 XA dash plus 800 1 minus XA dash corresponding to that. So this is already being shown to you. So say for example they happen to ask you at 450 torr. So at 450 torr you can find out this one also as well as this one also. So I hope you have enjoyed today's session. This is quite informative, and hope you have liked this equation, liked this discussion. And if you have not yet subscribed to my channel, do subscribe to my channel so that I could place more interesting uh, concepts in front of you. Thanks a lot. Have a nice day. Stay safe and take good care of yourself.